The power of a test. This video will discuss what the power of a test is in the context of a test of significance, why power is useful in a test of significance, and what factors can be manipulated in order to improve the power of a test. First of all, what is the power of a test? The power of a test is the probability that the test will reject the null hypothesis when a specific alternative is true. Now we're assuming here that the null hypothesis is in fact false, and rejecting it would be a good thing if that were the case. So power is a useful thing. If we can improve the probability that we're going to reject null hypotheses that are false, then that's certainly a good thing. It helps us to make correct decisions more often. Okay, now how does power get determined? Well, let's suppose we have a situation like this, where we have a null hypothesis that P is equal to P naught, and the alternative hypothesis is that P is greater than P naught. And this would be in the context of, say, a one proportion z-test. Okay, the null hypothesis view of the world is this: the sampling distribution of the sample proportion P hat is going to have a mean at P naught, because when we state a null hypothesis, that becomes the working assumption behind our test of significance. So the center, or the mean, of the distribution of all the P hats that we could get would be the null hypothesis value P naught. Now, we can choose any alpha level that we like. Typically 0.05 or 0.01 are the most common. And whatever alpha level we choose, there are some values of P hat that are going to cause us to reject the null hypothesis, because we'd be out here in the tail, our P value would be smaller than alpha, and we would reject the null hypothesis. Now, I'm calling the boundary line here P hat star. Any value of P hat that we get that is greater than P hat star would cause us to reject the null hypothesis. So getting a value of P hat that's greater than P hat star would be good in this case, because the null hypothesis is false, and if we were not to get a value of P hat greater than P hat star, we would fail to reject the null hypothesis, and we'd be making a type 2 error. We want to avoid that. Now, if the null hypothesis is false, there has to be some other state of the world that is true, and we're going to look at that next. This is the specific alternative value of P, the population proportion, according to the alternative hypothesis. Now, the alternative hypothesis in this case was that P is greater than P naught, and we've got a value here, PA, which is the true alternative value that is to the right of P naught. You can see we've got this distribution down here. It's basically that distribution shifted to the right. Now, if the alternative hypothesis is true, the true sampling distribution of P hat has a center at PA instead of P naught, and this would represent that sampling distribution. Now, what we're interested in is the power of the test. Okay, what is the probability that we're going to get a value of P hat that's greater than P hat star if this specific alternative value PA is the true population proportion? Well, we can calculate that fairly easily. The sampling distribution of P hat is normally distributed if the conditions are met, and it has this center PA, because P hat is an unbiased statistic, an unbiased estimator of the true population proportion. And we can calculate this using a simple standard normal calculation. We find the probability that we get P hat that's greater than this P hat star if PA is true. And that area under the curve to the right of P hat star would represent that probability, and that is our power. Now, over here on the left, we have this complementary event over here that's failing to reject the null hypothesis when PA is true. And that would be the probability right there of a type 2 error. That's what we call beta. And that probability of type 2 error, or beta, is complementary to this power over here. These two areas here add up to 1 because the whole area under the curve is 1. So those are complementary things, power and the probability of a type 2 error. Okay? Now, you can look at this diagram and you can see different ways that you could potentially increase the power of your test. One thing you could do is to make the difference between PA and P naught bigger. That difference is what we call the effect size. And if you increase the effect size, you can make the power of the test bigger. Now, people say, well, wait a minute. We're testing this null hypothesis. We have this very vague alternative hypothesis. How do we know that that specific alternative right there is true? Well, it's an educated guess. We think maybe we're doing a clinical trial here. P naught would be the value of the proportion of people who would get relief from a placebo, and PA is what we think based on scientific research, what we know about pharmaceuticals and everything else, that we think that PA is the proportion of the population that we think would actually get relief. And it's an educated guess based on, background information, science, etc. You can't just say what that's going to be arbitrarily. It's got to be based on some kind of realistic science. If that difference is bigger, that is, if this distribution is farther to the right, then this p hat star will be farther out in the tail of that distribution, and power will get bigger, and beta will get smaller. Okay. Another thing we could do is increase alpha. If we make alpha bigger, say by increasing our level of significance from 0.01 to 0.05, that would make this p hat star get smaller, and that would mean that this beta area down here would get smaller and the power area would get bigger. So that's something we could do. Now remember, if you increase your alpha level, that makes the probability of a type 1 error greater, and that could potentially be a cost. And then the third thing we can do is increase the sample size. If we increase the sample size, this distribution up on top will get narrower, and p hat star will move to the left, and this distribution down on the bottom will get narrower, and so the tail that's to the left of p hat star is going to get smaller, the area to the right would get bigger, so power would increase, the probability of a type 2 error beta would decrease. Okay, so again, an increased sample size is a good thing.